Okay, welcome to the session 7 of ARM development course. I am very happy to interact with you again. So in this class, before I start teaching you more on instructions, how to use them for different purposes, the most important thing is for us as a programmer should be able to provide some values or constants along with the program into our code, okay, for the instructions to execute. So that will involve these two operations, okay, where we may do some operations. The barrel shifter in the CPU may do some rotate or shift operations, or we will be providing some constants which will be used internally in the program. Now today we will concentrate only on what are the different ways ARM accepts the constant values and how it operates on them, okay. So this is the start of learning the instruction set, because this is going to be there in every instruction that you may encounter, especially all the data processing instructions will have some, may have some constants which are passed along with the instruction. So I thought first I will explain what are the different ways that can be provided to the instruction, and it will be mixed with any other data operations, okay. So I want all of you to pay attention to this. It's very interesting part of the instruction set, and I wish you will understand and follow this and then try out all this in your simulator, then our concepts will become much more clear, okay. So let us get into this. So you know what all different operations could be performed. You might have studied in your bachelor's course. Given a 32-bit data, what do you have in a register, we could do various operations on it. We could shift it to the left, the bit positions, or we can shift it to right. There are two ways of shifting. One is called logical and arithmetic. If you know, in arithmetic shift, the specific important thing that we need to pay attention to is the sign bit of the value. And all of you are by now familiar with 2's complement, I suppose. And for an example, if suppose you have a number, okay, 1 1 0, sorry about 0, so big, okay, assume this is a 4-bit number, you know that this is a sign bit, right. So if it is a sign bit, a signed number, it will be interpreted as a negative number. Then how do you find out the actual value? You find the inverse of all this and add 1 to it, which will be 0 0 1 1 plus 1 will be 1 0 0, that is minus 4, okay. Now suppose if I do a shift right, okay, what am I doing? I am making the MSB bit position to the lower side of the bits. That means I am actually reducing the value. If I right shift it by 1, I am actually reducing it or dividing it by 2, okay. So it should become like this, okay. When I right shift it, it should become 1 1 1 0. Now what is this value? You again do the same thing. Is it a negative? Yes. Even after shifting, it turns out to be a negative value because MSB is set. So how do you find out the equivalent number of this? You complement all of them, 0 0 0 1, and then plus 1 you do. Then it becomes 2. That means minus 4 here has become minus 2 here by shifting it by 1 bit to the right. So this is what is called arithmetic shift right, okay. So what you need to do is, when you are doing an arithmetic shift, you are interpreting this number as some binary number, and it could be a signed or unsigned number. So if it happens to be a signed number, you want to preserve the sign bit of the number. So when it is doing the shift, it should move the same sign bit along with the numbers. So effectively, that is the difference between arithmetic shift and a logical shift right. What is logical shift right? If you do a logical shift right, this will become 0, 1, 1, 0. So you are not preserving the sign bit. This is called logical shift right, whereas this shift is called arithmetic shift right. Now you may wonder why there are no arithmetic shift left. Let us try. Now when you want a number to be shifted left, you are actually multiplying by 2. Why? Because this bit position, whatever is the number, if it moves to the left, it is gaining more value. In terms of value, it is gaining more. So when you are shifting it this way, you will be filling it with 0 here on this side. So suppose this is the input, -4 you have taken, and then you are shifting it right left, you will be making it like this. So your back will the right side, it will be filled with 0. So it is same as logical shift left. That is why there is no separate logical shift left, but there are two different rights. It could be logical shift right or arithmetic shift right. Now how does the programmer inform the processor? They have to mention a particular acronym in the instruction so that processor knows whether it has to sign extend it or not. Okay. So this is very important thing you should be familiar with before we get into this. So I thought I will explain you this. Okay. Okay. Now apart from this, there are so many other ways this can be done. Different operations could be done. Let us see all of them in this class. Okay. Now let us first see what is the general format of a data processing instruction. You have to remember the data processing means it could be any of the operations. Even move operation is a data processing instruction, but it could be and I am not sure whether you will be able to see it from your seat, but I will read it out for you. These are all different operations: binary, boolean, operations, and exclusive or subtract or add with carry or compare or move. They are all called data processing instructions. Now what am I showing here? This is the format of an instruction. If you remember, the ARM instruction is of 32 bits wide. All instructions are of 32 bits. So you should remember that. Now where is this instruction stored? It is stored in the instruction memory, and it is stored 4 byte aligned address, and R15, which happens to be a program counter, accesses the memory and then fetches this particular instruction, any instruction which is there in the memory, and now after fetching it goes into the decode stage of the pipeline where this instruction is interpreted. Now for a decode logic to understand the instruction, it should have a standard format which is unambiguous, so that the decode logic will be able to understand what is being conveyed in this 32 bit of information, which happens to be one instruction. Now let us go one by one. Now what are these 4 bits? This is called conditional fields. What is this? If you remember, I mentioned that every instruction can be combined with a condition. That is, if that instruction needs to be executed or not, whether that instruction has to be executed always or it has to be executed only when some condition is met. If you remember, I mentioned that add EQ. That means add instruction will be executed, that addition will be performed only when 0 flag is set. So when that particular execution enters the execute stage of the pipeline, the processor looks at this 4-bit value, and based on this it decides whether it has to be executed always. If it is to be executed always, it should be filled with 1110. Otherwise, it has some other condition will be there, which will be comparing with the CPSR flags, and if it satisfies, it will execute the instruction. Otherwise, it will skip the instruction. So that is why the conditional flag is sitting here. Now what is this 00? It is implied that this is a data processing instruction, and then comes, so once it is a data processing instruction, the rest of the things are interpreted the different way. This is not the standard format. Maybe the RN and other register locations are fixed, but other bits will be modified or changed based on the particular instruction which is being considered, but it will be unambiguous between one instruction to the other instruction. So now we are showing, what I am showing here is the data processing instruction format, and then after this 00 is encountered, then it will know that okay, this is a data processing instruction which is coming in. Now let me see what is the value of I here. So this is I is an immediate operator. Okay, so if I equal to 0, it will interpret the 12 bits of the lower 12 bits of the instruction as a 8-bit shift operation followed by a register RM. Now if you remember again, RM is a one of the general purpose register. So how many registers we have in the ARM processor? 16 registers. So it could be interpreted as 0000 to or 4 ones. So 0 up to 15. So based on this number, it will either pick up R0, R1, R2 or R50, whatever is the instruction which is mentioned here. Now what is RM? RM is the second operand to the ALU. Okay. So if you remember, there are two operands that can be fed to ALU. One directly coming from the register file to ALU. The other one comes through a barrel shifter. If you remember again, the operation that barrel shifter does, it does it in one cycle, the first phase of the cycle, and then operand is made available to the ALU, the second operand, and first operand is directly read, and then the result is written back into RT. Now whenever I say RN, you should know that the operand which is coming from register file is directly fed to the ALU. It doesn't come through any ALU or any modification or barrel shifter or anything. Okay, so it is directly fed into the ALU. RM is the other operand which is called operand 2, will come through barrel shifter. Now barrel shifter also may do some changes to RM, or based on the instruction it may not have any impact of RM. It will be a short circuit, then RM will directly come into ALU. I will show you different examples where you will be able to map this with the actual instruction. Now what is the result coming out? That result coming out of the ALU has to be written into RD, that is a destination. So it could be written into any registers, one among the 16 registers that can be written into. Okay, so RN, RM and RD are all 4-bit wide in the instruction format. Now where is it located? RN is located here, RD is located here, and RM can be here or it need not be there. If suppose I happens to be 0, there is no RM mentioned, it is a direct immediate value. Now what do we mean by immediate value? The immediate value means it is part of the instruction. If you see it, this whole 12-bit content has come from the instruction. That means it is coded by the assembler into the instruction and it is kept in the memory, that is instruction memory, and when the processor was fetching the instruction, it has come along with that. Now if suppose the operand is coming from RM, then that means it is using, this instruction is using a already existing value in one of the registers as an operand. Okay, or it could take both things, that is some part of the instruction, some part of the operand is taken from RM, and then what operation need to be performed on the contents of RM is provided by the constant, that is it is has come with the instruction which is interpreted in a different way, and I will explain you in the subsequent session here today. So barrel shifter takes this value and accordingly it operates on this RM and then gives the result into ALU. Now how does ALU know what it is supposed to do with these two operands? Because it knows that okay, RN is coming from this number and RM is coming through barrel shifter or directly, but what is that arithmetic logic it is supposed to do? It could do add or subtract or move. That is what this opcode is for. This field, this is again a 5-bit field, 4-bit field. which will explain what operation it is supposed to do on the operands. Okay, so this much you understood. Now let us see what is this S for. If you remember, I mentioned that in the instruction you can say move or move S. When I say move S, that means that execution of that particular instruction will impact the CPSR flags, the conditional flags. Which are the conditional flags? Carry flag, zero flag, or negative, or overflow flag. So if this bit is set, suppose if you are mentioning in your instruction move yes, then assembler will set this bit 1. So then what will happen? The processor will know, okay, the programmer wants this instruction to affect the CPSR flags. So whatever operation is done, based on what is the result coming into RD, it will set those flags. Suppose if the programmer has not mentioned yes in the instruction, then assembler will interpret it and make this bit as 0. Then processor, when it looks at it, it will know that okay, this instruction is not supposed to impact the CPSR flag, so let me not change anything with the CPSR and do only the operation what is requested by this instruction. So this is the way the processor interprets the instruction, and this is the way the assembler encodes your assembly instructions into a binary format, and it fits into the 32-bit format so that processor understands that and accordingly acts on it. Okay. Now there may be two possibilities. In yesterday's session, in last session, I mentioned that the move instructions are single operand instructions. But you may wonder that there are two registers mentioned, but I say it is single operand. Please remember, here operand is only this R1. R0 is always this particular value mentioned here is a destination register. It is not an operand. Okay, R1 is moved into R0. So there is only single operand coming. Now please remember, R0 or R1 is anything. It could be from R0 to R15, any one of these, based on the values of RD. Now R0 is what? It is actually RD here. So if this instruction has to be there, R0 would have been, RD would have been coded as 0001. That means, sorry, all zeros. That means it is R0. And R1 is what? Always in a single operand instruction, that operand is assumed to be RM, not RN. So wherever RM is supposed to be, that place it will make 0001 to indicate that okay, it is a single operand instruction, and the operand happens to be a R1. So there will be 1 here, and to indicate that destination register is 0, there will be a 0 here. Now what happens to RN? RN will be ignored. Okay, how will the processor know that it has to ignore RN? Because RN also can have any value from 00 to 111. So it's a valid value. But based on the opcode, it will know that okay, move is supposed to have 1101. So if opcode is 1101, it will not look at this value here, and it will know that it's a move operation. So it doesn't have two operands, so it is RN is ignored. Now you may wonder why in a single operand instruction RN is not considered and RM is considered, because you have a flexibility here only with RM that you can do some barrel shifter operation before feeding that value into the ALU. Now for a move instruction, what is the need for ALU to come into picture? Because this is the way it is structured. So if it is a move, ALU will just pass on this value out to RD. So it will, RM will come if barrel shifter operation is required based on suppose some LSL or something else you have mentioned here, then it will operate on that R1 and then pass on this value to RD, and it will go to register bank again, back to register bank. So this is the way the ARM processor inside interprets your instructions. Now what about two operand? Is a simple example. R1 and R2 are two operands. Then you will be able to map it. R1 happens to be Rn. So in the location of Rn, it will have 1, and then R2 happens to be Rm. So in this location there will be 2, and RD happens to be 0. So RD will be 0. So and opcode will say that it is a add instruction. So wherever add is, it will say here 011 0100. So that opcode will be put. So that is the way it is interpreted. I hope you understand this. Now I have shown one more arrow here. This is a immediate value which is coming along with the instruction. Now you have to remember, when this instruction was fetched, it has come along with the instruction. Now this is executed after 2 cycles in the execute stage. That time this value is passed on to the pipeline registers and then made available to the barrel shifter by taking out this value which was there part of the instruction, and then it is fed to the barrel shifter so that it can operate on it. Now how this immediate values are interpreted is what is going to be explained in this session. Okay. Now let us go one by one. Now operand is actually this operand 2 field. This is completely a 12-bit field. Okay. So based on the value of I, if it is 0, it will be interpreted that a 8-bit value is used for shift related operation, and this is the register value, that is RM, which is the input to the barrel shifter. If suppose I happens to be 1, then this instruction will be, the 12 bits will be interpreted this way. That means the complete thing is immediate constant. There is no RM here, so it is not taking any value from the register. Everything is coming from the immediate constant only, and then some operation is performed by the barrel shifter on this immediate operand and then given to the ALU. So this is what you see as another arrow coming to the barrel shifter in the previous slide. Now let us see what all you can represent. Now immediate operand may be a register, as I mentioned. It could be a register or an immediate value. Okay. Now based on the I bit, it will decide. Okay, if it is I bit is 0, it will interpret this bit combinations as RM followed by a shift operation. Otherwise, it will interpret it as values like first 8 bits will be interpreted as some immediate constant, followed by what operation, rotate operation needs to be performed on it. Don't worry, even if you don't follow this fully, remember that there is a part of the field, instruction field, which is interpreted in 2 different ways based on the particular bit set in the I flag. That is enough. How it is interpreted with the actual instruction, I will show you so that it will become very clear to you. Pay attention. Okay, remember what I am showing, and then with a register you say 8-bit value of shift operation. Suppose you say that one operand is coming from RM, how many bits will come? 32-bit value will come from the one of the registers in the register file, and then you will perform a shift operation based on this 8-bit value. How this 8-bit value is interpreted, I will explain to you. If it is an immediate value, the 8-bit value is here, and then some 4-bit rotate operation is performed on it. So no RM is coming here. So there is no register content for doing a rotate operation. So the barrel shifter doesn't take any value from register file, but it takes only the immediate constant coming from the pipeline register and performs some operation based on the instruction. Okay, I hope you understand the difference between these 2 formats. Let us go forward. Now I am going one more deep level here. I mentioned, okay, one operand is coming from RM, that so some operation the barrel shifter is supposed to do on the contents of this 32-bit value. If RM happens to be 1, that means R1 contents are taken. If it happens to be 2, the R2 contents are taken. Now what shift operation needs to be performed? That is interpreted in 2 different ways based on this bit 4. Okay, this bit 4 could be 0 or 1. Then suppose let us go to the left part of the format. If it happens to be 0, then next 2 bits are interpreted as one of these operations. Okay, either logical shift left or logical right or arithmetic right or rotate right. I told you about these instructions, how they differ. So based on these bit positions, bit values, it will interpret it as one of them. And then these 5 bits are considered as a 5-bit unsigned integer. Please remember, it is an unsigned integer. So it could change from 0 to 31. Now based on this value, it may do that many number of either logical left or logical right or any of these operations on RM contents. One example I will tell you. Suppose RM happens to be a 0. What does it mean? It's a R0. That is, content of R0 is taken. Now assume that this bit positions were 0 0, then logical left has to be done. Now okay, it has to do a logical left shift. Okay, that means it will fill the left to rightmost point bit position as 0. Now assume that this 5 bits happen to have 2, a value of 2. Then what it will do? It will take the contents of R0, whatever is the value in R0, it will left shift by 2 bit positions, and then that result will be used as an operand to the ALU. Please remember, it is after this operation, it is taken as a second operand to the ALU. Now based on the opcode, it will be taken and then that particular operation will be done and then the result will be returned back into RD. Now assume if it was in this format, then this is 1, so it will interpret this as a shift operations or this needs to be done, but instead of interpreting this 5 bits as a some 5 bit shift operation, it will take this as the RS. That means it is pointing to one of the registers. Okay, it could be 00 to R41, so that means it can be R0 to R15. But there are some restrictions that R15 can't be used here. But I'm telling you, possibly that there one of the registers are used, and then it will interpret the lower byte of that register has to be taken as a shift operation. So please keep in back of your mind that the interpretation is different based on the bit positions, the values of this bit. So how it is performed, I will show you with examples so it will become clear to you. Okay, let us go forward. Now we are going to concentrate on this part of the combination. Okay. Now I have taken only that portion, so you don't have to worry whether it is same or different. Now you are doing any of these operations based on the instruction, and then the shift amount could be 31 bits, which will be sitting here, and then logical right fills with logical right. Okay, the bit positions are shifted to right, and then the MSB positions will be filled with 0. If it is arithmetic right, as I mentioned, it will be filled with the sign bit. It will be extending the sign bit value. If it happens to be 0, it will fill it with 0. If sign bit happens to be 1, it will fill it with all 1s. No arithmetic left is needed because it is same as logical left. I explained to you already. Now let us go one by one. I told you that in this particular combination what we have taken, RM is coming in. One of the RM register contents are taken in. Please remember, it is not saying RM, so contents of RM. That means the RM values are not disturbed. It is copied and then barrel shifter does some changes to it and then feeds that value into the ALU as an operand 2. Now how much to shift? It takes it from the 5 bit value which has come along with the instruction, and then based on the 2 bits it will do a logical shift. Now in this case we are taking an example where logical left is 1. Now logical left is this content will be shifted left. Now logical means anyway it will be backfilling it with 0, and then whatever bits going out, they may affect the carry or may not based on whether S bit is set. That means if you have mentioned a S in your instruction along with this logical shift operation, then the last bit which has come out of the shifting may sit in the carry flag. Okay, the least significant bits of the results are filled with 0. Okay, you can see this, and then whatever bits go out do not map to the result are discarded, and the last discarded bit which becomes the shifter carry output which may be latched onto the C bit. Okay, I will give you an example so that you will understand. The last bit coming out of this will latch on to carry flag provided S flag is set. That means if you have mentioned the S in your instruction, then it will set the carry flag, otherwise it may not. Okay, so let us see an example. Okay, it will become clear. Now I will show you how the coding what I mentioned is done here with one instruction, then the rest of that you will be able to deduce it by with the help of the simulator. I am taking an example of move S. First let us understand what this means. Precondition and post condition before this instruction is executed. Now precondition is assume the carry flag is 0, okay, and then R2 is already filled with the value all S, okay. Now I have an instruction to say move S R1 comma R2 comma LSL #1. Now what is this #1 means? It's an immediate constant coming with the instruction. It is coded along with the instruction. Okay. Now let us see how this instruction is coded and where this how these bit fields are filled. One instruction, if you see how it gets filled, the rest of it you will be able to understand. Now, okay. First of all, is there any conditional thing mentioned here? If it was move EQ, then EQ condition is mentioned. That means it should execute only when 0 flag is set. But here I have put a move S. That means I don't want this instruction to be conditionally executed. Okay, so it should be always executed. So the conditional part of that instruction will be 1110, which is meant for always, because it is going to be executed irrespective of whatever may be the conditional flag status of the conditional flags. Okay, now because it is a move instruction, it's a data processing instruction, but so this will be 0. Now see here between it is changing, okay. Now this I is interpreted as 0. Who is doing this, filling this value? Assembler, okay, or it could be a compiler if it was C source file was compiled and then it generated a move instruction and then the obj file would have put this value. But if you have written an assembly code, let us for our example, let us assume that you have written an assembly like this, then the assembler will generate this particular format based on the instruction what you are given. So it has put a I as 0 because you are interpreting it as an immediate constant, okay, and then why you are mentioning a register here Rm which will be 0, okay, and then you have mentioned R1 here which is a destination register. So you mentioned R1 here, so RD will be filled with 1, and I have mentioned S here. So I want this instruction to impact the flags. So the assembler has promptly put a 1 here, and then I mentioned that it is a move instruction. So it has generated an opcode which happens to be 1101 for move. So far so good. Now you may wonder how it has filled 0 here, because it doesn't use another format. It's an immediate constant format, so it has to be a 0. Now why it has put a 0 and I call it as a don't care, because move instruction doesn't interpret or take this value Rn at all, because it is interested only in one operand which is R2, which is passing through the barrel shifter which happens to be Rm. So Rm is filled with 2. Now you see here it is a single operand instruction, so it was filled with 0, but it won't interpret as a valid value, and then it knows that R2 is the second operand, so it has filled the 0010 here. Now it has to interpret this. You have mentioned that it is a logical shift left. So if you remember previously, the LSL, these 2 bits happen to be 00 if it is a logical shift left. So it has filled promptly a 00 value, and then it is left with only filling this constant. It is given as 1, so it has filled to 1. Now I'll ask you one question. Suppose you have mentioned LSL #0x02. That means you want 2 positions, you want to shift the logical shift left you want to do on the operand 2. So this 2 will be reflected by filling a value 2. So can you write some 45 0x7f? You can't. because you have the maximum 0 to 31 here, because 5 bit only can be filled into this constant value. So you may wonder, if I give by mistake hash 0xFF, a big number, assembler will give a warning that for this instruction you are allowed to give only between 0 to 31. So based on that, assembler will make sure that these kind of wrong instructions don't even come into the program. So because if it cannot generate the code for your instruction, then it will give a warning. So this is the way the instruction is coded. So I have explained it for one instruction, and I urge you to not to interpret every instruction that you come across, because then you will be behaving like an assembler, which is very laborious job. But if you do one or two instructions and then see what is the binary code generated for a particular instruction, it will give you a better idea. Now you may wonder, how do I know where this particular format is? I will share the instruction for document, ARM instruction set for document, which explains for every instruction what is the format followed. So you can then write a code like this and then look at the generated binary code in the simulator and try to expand that value into bit positions and then map into these positions so that you understand what it generates. If you do it for one or two instructions, you will be familiar with anything and you will be very comfortable doing it. You may wonder, why is it required? Anyway, assembler is doing, why should I bother about these kind of bit level values? I'll tell you, when you have to debug your code at the assembly level, at the binary level, there are some occasions where you may encounter the program crashes, or it generates an unknown instruction, or it generates abort, data abort. In those kind of situations, there may be a memory corruption in your embedded processor, or there could be ROM can be programmed wrongly. So if you can understand the binary format, then you have a good handle on how to interpret what is stored in the instruction memory. So you do it for one or two instructions so that you become familiar. Later on, if it is required, you will be doing it. So this is the value actually the simulator has generated, and then I have expanded it like this and explained to you. I hope you understand it better. Now let us see what is this actually performing. Now R2, I said that all F's are there. That means all bits are ones. Okay, all ones. Now you are doing a left shift, logical shift left by one bit position. That means all ones are here, and then you shift out only by one position. And then you have mentioned also that S is there. That means it is supposed to impact the carry flag. So what happens? The last bit which is coming out of the shift happens to be a 1, because you are doing only one left shift, and then this bit 31 happens to be 1 because F is there. That means that 1 will go into the carry flag. So if earlier carry flag was 0, you will see the carry flag is set. Now once S is there, it may, based on the result in R1, the other flags are also set. But please remember, only 0 flag and negative flags are set, and overflow flag is not disturbed, because it is not anything to do with the arithmetic operation. So now N flag will not be set. So you will see that 0 flag is 0 because the result what you get by shifting it is actually FFFE. That is, this value is 1110. Okay, because it is backfilling it with a 0, and you shifted it by only one bit. So 10 will enter in the value. So whatever is the shifted value is moved into R1. That's why you see that R1 is having all F's only with the E. The lower nibble is having 1110. That means the LS bit is 0. Okay, but R2 is not disturbed. It's same as what was there earlier. And these flags are set because this result is in MSB is 1, so negative flag is 1, and it is not a 0, so it is 0 flag is 0. So I have taken so much time here to explain this. I hope you are able to understand it. Then we can go a little faster in the next set of examples. Okay. Now let us see. I want you to hold on to this presentation and try to interpret it yourself. what you see is correct or no, then maybe listening to me will be better. Now what is the position here? Also the instruction says I want this to affect the carry flag or 0 flag or negative flag, and then R2 is filled with a 0 1, and that is the operand RM, and left shift logical shift left by 2 position, that is 1 is moved to 2 position, that means 1 0 0 it will become, right. So what is 1 0 0? It is 4. So now one R1 is having 4, R2 happens to be same 1, and then carry flag and 0 flag. I am not going to explain further. I hope you will understand this. Okay, let us go to the next one. One more thing for this particular format, you are supposed to give the conditional thing if that is required first and then followed by a yes. So this is not accepted as a valid instruction in our assembler also, in our simulator also, and I think this is the standard format followed. So operand, what operation needs to be performed, and then if conditional things are there, EQ, NE or AL, whatever, give that, and then yes flag if it is required. So this is all optional. If you want to mention the condition and then whether you want to impact the condition flag, you have to mention this. Yes, okay. That now there is some unique thing. LSL 0, if you say logical shift left by 0, that means you don't want to do any logical shift at all. In that case, what happens is the previous carry flag is carried forward, that means it is kept as the same, and then it impacts the other flags. Okay, it's a special condition. When you say 0, you don't want to really do any operation on the RM. It is a short circuit. Barrel shifted is not doing anything with your operand, so it will interpret it as a no operation to be performed. So take an example. R2 is the operand to the barrel shifter, so R2 is filled with all ones. So when you do no shifting, it will pass through the same. So when it comes into R1, it is same as R2, but carry flag was 0, so it keeps the same value, and then S was there, so it is disturbing the other 0 and negative flag, because the result happens to be FFF, 0 flag is 0 and N will be 1. Okay, so when you have a hash 0, that means you don't want to do any shifting of left operation, so it is a pass through to the barrel shifter, and carry flag is preserved and the rest of the 0 and negative flags are modified. Okay, so whenever you mention this kind of instructions in your code, you should know exactly what you expect the processor to do. Otherwise, you will have you will not be able to understand what is happening in the processor. Okay, so these are all about logical left shift. Now let us see logical shift right. Okay, it is very simple. You do the shift operation to the right side of whatever RM comes, and then backfill these values with 0. So when you are right shifting, you are reducing the value which was in RM. So by reducing it by 2, if you are right shifting it, but it could be some bit pattern also. It may not be a binary value. You may be trying to create a pattern in your register value. So you may do a right shift, but whatever is the last bit going out may impact the carry or not based on the S flag. So this also has the same condition as LSL 31 0 to 31 as a constant value. You can mention LSR as the operation to be performed, and the last discarded bit is either affecting the carry flag or not based on the S bit set. That means whether you mentioned yes or not in the instruction. I hope you understand this. It's the same replica of left shift. Only thing is the bits are now moving to right. Now let us see an example. The N is mentioned here, LSR 1. Now take an example. The R1 is initially filled with 1, and then it is shifted by right 1 bit. What happened? This 1 bit, what was 001, goes out as a carry flag, and S is set, so it will impact the carry flag. Okay, but now backfilled with 0, so R1 has only 1 bit set, so it is gone out now. So R1 will be left with all zeros, which is copied into R0. So R0 will have 0. R1, please understand, R1 will not be disturbed. So R1 value is same. Only thing is that value is taken and then shifted right. Okay. So Now why carry flag is set? Because that one bit which went out is supposed to impact the carry flag because S is there. So carry flag is set. Now why 0 flag is set? Because you are having the result which is in R0 happens to be a 0. So it is set. Now why N flag is set? 0 because there is no MSB set. So this is the outcome of LSR. Now let us see one more example. You have R2 which is one of the operands for the barrel, only operand to the barrel shifter, which happens to be 4. That means 0x4. Please remember. So that means 1 0 0. Now when it is shifted to the right, 1 0 0 will become just 1. So that's why that shifted value which is moved into R1 happens to be 1, and R2 remains same, and the carry flag why it is becoming a 0, because what was shifted out was a 0. Last shifted out was 0 only, because it was 1 0 0 which 2 zeros went out. So that 0 flag is set, 0 coming out of the shifting is sitting in the carry flag because S is set. So that is 0, and then 0 flag is 0 because the result is not a 0 value, and N is 0. That's it. Okay. I hope you now understand how to mention LSL or LSR in your code and how to perform it on the RM register what you have. Okay. Now let us see some special interpretation of LSR 0. Please remember, LSR 0 means what? You don't want to do any shifting at all, right? But I also told you LSL 0 which did not want to do any shifting operation. Now when you don't want to do any shifting either left or right, how does it matter whether you put LSL 0 or LSR 0? Both are same. So the ARM processor community, the designers have had a very innovative idea that they wanted to use the LSR 0 as to be interpreted as something different that you are interested in doing. Because as a programmer, if I don't want a bit pattern that I have in the RM to be not to be disturbed, I would have mentioned LSL 0. So I don't have to have two options to mention the same thing. So they used this LSR 0, that is logical shift right. If you say it is 0, they don't want to interpret it as again, okay, I don't want to do any shift left right operation and I want to pass on the same value of RM into the ALU. So they used this pattern for some other purpose. So internally assembler will put a 0 only in the constant value, but it will say that it is a LSR operation. Then the processor understands when I have this, the processor is supposed to perform a 32 bit of write operation, bit position. What does it mean? It will perform a write shift by 32 bit positions. Okay, what happens? When it moves all the bit positions by 32 values and it is backfilling with all zeros, it will wipe off the whole value bit positions in the processor and make it as a 0, right? So which has a 0 result. Okay. So and then what will happen, carry out will be the bit 31 coming out. So if the instruction had a S bit set, then it will take out that bit and put it in the carry flag. So what ARM designers have done is, if you really want to do this operation, I want to right shift the whole bit and I want to backfill everything with 0, and then this MSB bit I want that to be impacted by carry, that should be written into carry flag. Then you are supposed to write a code with S there and then say I want to do LSR 0. Okay. Let us see an example. If I say LSL 0, it is same as what I explained to you. It will not have any impact on the parameters. It will pass on the same thing, and then carry flag whatever was there, it will reflect it and 0 and negative flag, it may change it based on the result. So you have to use LSL 0 when you don't want the parameter to be not, the RM values to be not to be disturbed before passing on to the ALU. But if you want LSR 32 to be performed, then you write LSR 0 there. You may wonder, why can't I write LSR 32? Because you cannot write 32, because 32 is cannot be fit into the 5-bit value allocated for this constant. So assembler will crib. So it will give a warning or error, suppose it will give a error. So if you write LSR 0, it will interpret internally, the processor will interpret internally that you are interested in performing this 32-bit of right shift, and it will do this. Now take an example. Suppose if R2 was filled with all ones, and then I am calling this move S R1, R2 LSR 0. For a simple programmer, it may look like I am not doing anything, no shift operation right, I don't want to do anything, shift 0, and I am supposed to get R2 as R1, but you are not going to get it. It is internally performing a 32-bit of right shift, and it will fill all the values that we had ones with zeros. So R1 will be having a 0, R2 will anyway be intact, and then the last MSB bit, which was happens to be 1, went out of the register, and because it is saying I want to impact the carry flag, it will be written into carry flag. So carry flag will become 1, and result happens to be 0. So that 0 flag will be 1 and N will be 0. Please remember, you should know the difference between these two. They are not same. And why they have put it in a different format? Because they don't want to waste one combination which does the same job as the LSL. So this is a very innovative encoding of instruction. Okay, I hope you understand this difference. Now let us switch over to arithmetic right. Okay, you will represent this as arithmetic shift right. Okay, now I mentioned to you in the beginning, it will, whatever is the sign flag, that sign bit, okay, MSB bit will be copied on. That's why it is shown like the same thing is coming here, and then whatever goes out, either the last bit going out will be affecting the carry flag based on what you want to do with the carry flag. If you want that to affect it, then you have to mention yes. Now let us take an example here so that you make this concept is clear. I have not put S here. That means I don't want this bit going out of this right shift to be impacting the carry flag. So then what I want to do, whatever is the content of R1, this is the content of R1, I want to do a arithmetic shift right by 1 bit. Now what is C? C is 12, okay, hexadecimal. 12 is represented by how? 1, 1, 0, 0, please. Okay, you should be able to, just when you see the assembly hexadecimal value, you should be able to just get the value. Okay, C is 12, that is 8 plus 4 is 12. So 110 is the last nibble. Now when I do arithmetic shift right by 1 bit, this will become 1 and this will be 0. So what is this value? It is E, right? So your R1 shifted value is moved into R0, which happens to be FF of E. Because why it is FF? Because it is doing a sign extension. So it is arithmetic shift. So it will be filling it with the ones. So you will get FF of E, and R1 you will see the same, and flags are not affected because there is no yes. I hope you understand this. If you don't, please listen again. 1 second. Let me erase this. Okay. Now let us see one more example so that you understand it fully. R2 is filled with 4 and I am trying to do a arithmetic shift right. Now what is the MSB here? What is the sign flag of this R2 here? It happens to be 0. So when this is copied and then shifted right, it will be backfilled with a 0, and it is shifting it by 2 positions. So 1, 0, 0 will become just 1. So R1 will become 1, R2 will be 4, and the flags are not affected because you didn't want the S here. So this is not going to impact the flags. I hope you understand this arithmetic shift right, and arithmetic shift right, okay, with the RM value. Okay, let me tell you, there is one special condition again here similar to LSR. The reason being, they wanted to make use of this pattern ASR 0 again. If it conveys that you are not doing any operation with shifting, you could have used LSL 0, right? So ASR 0 is again interpreted as ASR 32. It is same as the previous one what I showed you, LSR also. Okay. So ASR, what does it do? If you have mentioned ASR as 0, it will do a 32-bit of arithmetic shift, because it is different from 32-bit of logical shift. Okay. Let us take an example. Suppose you have mentioned R1 happens to be 8 all zeros. 8 means what? 1 0 0 0. That means MSB is set to 1. This is the RM. So that is a parameter operand which is passed to the barrel shifter, and it says ASR 0. Actually, it is not performing a 0 arithmetic. That means no shift at all. It is performing a 32-bit of arithmetic shift to right. So what is arithmetic shift right? It is supposed to backfill it with the carry flag. Now because carry flag is set here, it will backfill it with all ones, and it will do it for 32 times. Then that one would have propagated all through the register, okay, and it would have had all would have become 1 now, okay, and this carry also will come out. But because I mentioned as no S here, so it will not impact the carry flag, but R0 will be filled with zeros. Okay, it is a very easy way of doing a 0 here. Okay, so when you have this value and then when you do a arithmetic shift right, 0, it is doing a 32-bit of arithmetic shift right. Okay, so why ARM has decided to use this hash 0 as 32-bit shift? Because 32 cannot be written into it, and 0 if you write it is same as LSL 0. So they made use of that particular combination to perform this operation. Okay, let us see one more example. If suppose move S is there and R1 is filled with, see please remember I am taking only R0 R1. It doesn't mean that you can do only with R0 R1. You can do with any register, please remember. But R15 is always a special thing because it's a PC, but you can free to use R3, R4 or R5 or any operand. It could also be the same operand. You can say R1 comma R1, no problem. Why? It is always before doing any arithmetic operation, it is copying the value from register. Okay, so you can as well write into the same register. Only thing is the previous value will be overwritten, but you are free to use the same operands here. The R0 comma R0 is a valid instruction. Please remember that. You try out multiple combinations so that you understand that. And now ASR 0 you have mentioned. Then what happens? It is 1100. C is again 1100, which will go through all the bits. So it will all become 1. Then finally that MSB bit is coming out as 1, which will impact the carry flag because I mentioned yes. Okay, because earlier it was 0, it will become 1, and the other things are you can interpret it because R0 is this value, so this will be the state of the carry flags and the negative flag. I hope you understand this uniqueness of this instruction. Let us go to rotate right. It's another logical operation where you still now what we were doing is a shifting of the bit. It all the bits were going out, and then the last bit which was going out was either impacting a carry flag or not. But suppose if there is a need for you to rotate the bit, that means you want the LSB bit to come back into 31, then there is a provision for that. Now only rotate right is there, because you may wonder why rotate left is not there, because it is not needed. If you want to do a rotate left by 1 bit, you could do the same performance by rotate right by 31. So no, you can always do the same what you want to do. Maybe you may have to do so many rotations, but it doesn't matter. So you can do it with only rotate right. So there is only rotate right which is supported. And please remember one more thing, the uniqueness of barrel shifter is that any of these operations are not performed in multiple clock cycles. It's all done in single phase itself. It doesn't matter whether you are rotating it by 2 bits or 5 bits or 10 bits or 30 bits. Okay, everything is done in a single phase of clock, a single clock cycle. So it doesn't take more time to perform more rotation. Please don't think that if I do 10 bits of rotation, it will take 10 clock cycles. If I do 5 bits of rotation, it will take 5 clock cycles. Please don't think that way. It's all, the barrel shifter is designed such a way that any number of bit rotations can be performed in a single phase of the 2-phase clock cycle. Okay, so within a cycle, this barrel shifter does the job and then feeds that value into the ALU for ALU to perform the operation. So this constant what you mentioned doesn't impact the number of cycles the instruction takes. This is a very important point which I am not mentioned so far. I thought it is the right place to mention it. Please keep in mind this. Okay, let us see an example of rotate right. Suppose you have a R0 with a 1 and you want to do a ROR with 1 bit. That means you want to rotate it by 1 bit. What happens? This 1 bit which is LSB has to go out and then sit in the 31 bit position. Okay, so when you do this operation, R1 which is a destination register becomes 8000. Why? This 1 bit which LSB came out and sat as a MSB bit, because there is no S. I am not showing a flag, otherwise it would have set a two things. It would have set a carry flag also, because this 1 bit which was going out will impact the carry flag, and because it comes and sits in the MSB bit, it would have set the negative flag also. N flag also would have been set, but 0 would have been a 0 because the value is 1. It's not a 0. So because S is not there, the flags are not impacted. So rotate operation is performed. Okay, I hope you understand this. Let us see one more example to make your understanding clear. I have put a move S here, R1, R0, ROR 02. That means this bit position 0011 is the nibble, lower nibble, which is rotated by 2 bit position. That means both the 11 will come out and then they will enter into this bit. It will become 11 here. So it is effectively a C here. So the result R1 will be C, all zeros, and then the flag will be 1 because carry flag will be set, because last carry last bit which went out happens to be a 1. So it will be set, and N is set because MSB is set, and 0 is 0. Okay, so this is all about rotate. Now again, in rotate ROR 0, again, now you can mention that I don't want any rotation at all with this, by mentioning 0. But again, ARM interpret this as a separate instruction. It's a unique instruction which is called rotate right extended. Okay, it is same as LSR, ASR, and ROR. For all of these instructions, there is a 0 is interpreted as a separate instruction. So what does it do? ROR 0x is interpreted as extended, and what I mean by extended means it will take this 32 value of RM into as one 32 bit value, and then the carry flag as a 33rd bit, and then it does a rotate right. How many bits it does? It does only 1 bit. It is basically to bring in the carry into the value, okay, and throw that value which was LSB into carry bit. So it is basically carry bit is also considered as along with the 32 value, and then it does a 33 bit of rotation. Actually this bit going out is sitting in carry flag, and then carry flag comes into it, so you can call it as a 33 bit of quantity of right, but it is just only 1, because you have only one constant, and you can't mention that I want to do this n number of times, where there is no place for you to code it, for the assembler to encode it. So it will only interpret it as a 1 bit 33 bit of right shift or rotate. Okay, so take an example. Carry flag was 0 and C001 was there. This 1 will go and sit in carry flag, okay, and then this C11 will move into 0 1 1 because carry flag will come in. So it will become carry flag will be 1 and then it will become 0 1 1 all 0. So that 0 1 1 0 is a 6 actually. You know, if so R1 will become 6 or 0 and carry flag will be set because this one LSB went out as a carry bit and the result will be like this. So this is called rotate byte extender. So if you want to mention this, you have to mention this ROR hash 0 if you want to perform this operation in your assembly for some purpose. Okay. So this comes to a end of all the rotation. So 1100 becomes 0110, which happens to be a 6. Okay, now let us go back to our original operands, how they are interpreted. So far what we have seen is this part of the story. Okay, this part of the story we saw all the logical left, logical right, arithmetic right, rotate right, and then unique hash 0 was there in each of them, how they are interpreted as 32-bit values or right rotate extender. We saw for this part of the interpretation of the code. Now what is the difference between this and this? In this case the barrel shifter was getting the shift operation anyway part of the instruction. Both are actually shift operation. What needs to be performed is anyway is part of the instruction itself, but it was interpreting this as a 35-bit constant value which is coming in as into the barrel shifter through the instruction, and then it was operating on the RM value based on this how many bits have to be rotated or shifted left or whatever. Now suppose I want to do more than a 31 bit of operations. Okay, it had a restriction that I cannot give a rotation or a shift left beyond 31 bit values, right? If I want to rotate it by say 45 bits, you may wonder why is it required, but there may be, I will tell you, how it can be interpreted. But if that needs to be performed, this instruction format doesn't allow me to do. So there is a way to do it. Means you have to use one more register which is called a RS, a shift register. You can mention that one of the registers as a shift register and then put this how much of shifting or rotating you want to do in that shift register. The lower LS byte of that shift register, you mention the value, then the processor will read it from that and then perform that many kind of operation. So it will perform all the operations that you are want to do, but only thing is it will take that constant shifting operation. How many times it has to be shifted? It will take it from the RS register and that also from the lower byte of the register. Please understand this. Okay. Now let us see the different combinations of this. Let us go a little faster because it is simpler. So you can mention any register as RS except for R15 of course, and then suppose if you say RS if it and the RS has 0, suppose you mentioned as R1 and then R1's LS byte was 0, it will not perform any operation, it will just quietly come out. Means it will pass on the value of RM without making any changes to it. Okay, and then if value is between 1 and 31, it will be similar to whatever we have seen so far. Okay, so it will be behaving the same way. Only thing is you will be using up one more register for your for this operation. Now where is this format is useful? Only when you want to do some operation which is more than 31 bits. Let us see some examples for it and how to how to mention it. Now here again move is a single operand instruction because it only takes RM as an operand, but only thing is R0 is actually for the barrel shifter to operate on R1 and then pass on the value to R2. Now assume that R0 was having a value 1. Okay, now R1 is having a 0 2. This is the value. Now what is this instruction is saying the processor is take the value which is in R0, the lower byte value, okay, and that many times you perform this LSL operation, okay, on R1 content. Okay, take a R1 content and then do a left shift, logical shift left by as many times that is mentioned in R0 and then write the value into R2. Now for this combination of the value, what is it supposed to do? It is supposed to do a one bit of logical shift left, which of this value, because R1 happens to have 2. If it logical shift left, if it does, it will become 4. So R2 becomes 4. R1 and R0 are not changed. Okay, please remember these are all treated as a inputs to the barrel shifter. They are not modifying them. So if you write the instruction like this, instead of immediate constant, you are mentioning a register, then it will take the value from the register. So this R0 can be any register again, and now it could be same as other para operands also, but you should be aware of what you want to do. Okay, I urge you to change these parameters, give all of them same or different, and then initialize these registers with previously with some values, known values, so that you understand what is happening with the instruction. You have to try out multiple combinations. There are so many combinations available. So you try out all this so that you understand what happens with the different instructions. Now another example I have given you, LSL R0. Now R0 is filled with F1. F1 is what? It is a huge number. Okay. So that many times it wants to do a right shift, left shift, logical left shift. So it is equivalent to doing it over and over again. Now what happens? RM, when it is copied, the R1 value is happens to be 0 to 2 to start with, but once it does a logical left shift, it will be filling it with all zeros. So effectively will be performing a rotate operation, left shift operation, so many times. But actually inside the processor, there is no point in doing that rotation blindly more than 32 times, right? So it will effectively give you the value which what you will get likely to get when you do this many times, and then it will reflect the value. So in here, what happens? It will be all zeros, and then flags are not impacted. So that is what you will get. Now what happens here? Another example, arithmetic shift right with a Z R0 happens to have a 1 F1, that means this 1 will be filled with all bits, so you will get effectively all FF in the R2. Okay, that's what you see. Now there are some unique combinations. LSL by 32 has a result 0. Why? Because it will be filling all the bit position with the 0, so you will have finally end up with all zeros in that bit position. Okay, and LSL by more than 32 has result 0 and carry out also 0. The difference between these two is the carry will be 32 bit, the MSB bit will be carry bit. If you do it more than one time, then you will get all zeros, so carry will be 0 here. So I want you to try out all these combinations and see it yourself what happens. Okay. LSR 32 has a result 0 with the carry which is coming out of 31 bit as out of RM, will set the carry based on whether you have put S or not in the instruction. LSR is the same as the LSL, only thing is all will be 0. ASR will have the sign bit extended to all through the bits, and the last will also be based on the carry MSB set or not. You will have a carry bit set or not based on S flag also. Rotate right, that's the same thing, but it does more than 32 times. Okay, so what effectively, when you write a value which is more than 32 in a register and then give it as a parameter, it actually does a n mod of 32. Okay, effective what you see will be after one rotation is done, it will be n mod. So please remember, it will do the 32 bit of operation and then n mod. So it's not just a n mod. So it will do completely 32 bit times, and then the result will be what you see. So effectively it will be all zeros or carry bit. Okay, maybe I should remove this n mod, because you may think that it will do only n mod. Actually no, please remove this n mod. It will do 32 times, and then whatever is remaining bit is there, it will do the rotation and leave that value. It will be either all zeros or all ones based on the carry flag the MSB bit was set. Okay, so these are all about the combination which was mentioned as 0, that is one of the operand was coming from Rm. Now another combination is when you have everything is mentioned as an immediate value. So it's a special condition. That means this Rm is not used at all, because if you see in this combination there is no Rm mentioned here, and this 1 is actually I bit. Okay, if I bit was set to 1, this 12 bit is interpreted as some rotate operation on some immediate constant, which happens to be a 8 bit value, and all of them is coming from the instruction as an immediate value, and no Rm is taken. That means no register contents are taken for the barrel shift operation, and then it will perform the operations based on the bit positions which are mentioned here. Now let us see how this is interpreted. These 12 bits are interpreted as lower 8 bits are for immediate value. So the shifting operation is taken from this value, whatever you mention it as a this byte value, and then how much to do a operation is always rotate here. Please remember that it is always rotate, and that is also rotate right. Okay, so I'll tell you how it is interpreted. This value whatever is mentioned is multiplied by 2 and then taken as a rotation, and then used as an operand 2 for the ALU. So if you don't understand now, please wait. In the next example you will be able to understand it. Only thing is you have to remember that this is another format based on this bit position. It will be interpreted in a different way. Okay. So there is no Rm here. It is an immediate value with a rotate, some 4 bit content saying that how much to rotate. Let us see. First of all, let us try to understand the problem here. An arbitrary 32 bit value. Suppose you want to fill a register with an arbitrary 32 bit value, you can't do it, because you have a restriction that the whole instruction itself is 32 bit. How can you fit in another arbitrary 32 bit value into it, because an instruction cannot go beyond yet one 32 bit value. Okay, you can't have a 8 byte instruction, you can have only 4 byte instruction. That means instruction length cannot be more than 4 bytes, because it's a RISC architecture and we didn't want to complicate the ARM processor. Decode logic should not be complicated, because varying length of instruction is similar to a CISC instruction, right? So if you want to pass on a huge constant into an instruction, that can't be done, because you can't fit in a 32 bit constant into a 32 bit instruction. So there is a restriction that you can give a 8 bit value and then say some bit rotations, so that some value of 32 bit constant can be copied into a register. Let's see how it can be done. So the instruction allows 12 bit of location, so you use the 8 bit value here as an immediate constant, and then use the 4 bit to give some instruction to the barrel shifter. Hey, you do some operation on this immediate 8 bit value, so that I get the pattern that I want. Okay, so what is that rotate I want? I want the rotation to be performed on this 8 bit value. Okay, and when you are doing it, please 0 extend this immediate value. Okay, don't do any sign extension, because I am giving only this 8 bit value. So the barrel shifter needs a 32 bit input. So extend this 8 bit value into all zeros. So the MS part of it, most significant part of it will be filled with zeros, and take only this 8 bit that I give you, and then rotate it by this many number of times as I mentioned to you. So suppose it is not the same number of bits positions I give. This 4 bit position, suppose I say 1, please take it as a 2. If I say 2, multiply it with the 2 and then I understand it as a 4 bit rotate. Okay, and do the rotation on this 8 bit value that I have given you. Okay, still if you don't follow, don't worry, with the next example you will be able to understand. Now suppose I want to write this constant into a register. Suppose move R0 comma hash 0x000ff. Now this is a 32 bit value. Okay, actually it is a 32 bit value. Now what does assembler do? It looks at the value and it knows that okay, the most significant the information is in this ff. Only the 1 byte of value is is very important. So let me take that immediate value, that 8 bit value, into this location, and then say I want to rotate it by 0 times. So what the barrel shifter does, it takes this FF internally, 0 extends this value to 32-bit value and then doesn't do any rotation. So effectively you have got a 32-bit value getting as an operand to the ALU, and if it is a move instruction, it will be just passed on to RD and then it will move into the register R0, what I mentioned to you. So effectively the ARM assembler allows you to give a 32-bit value, but there are some restrictions. It can't be anything that you think you want to do. Now suppose you want to do this constant value. Now how can this be constructed internally? Because you are giving this FF, but when it is interpreted into the instruction, it will put this FF and then 0 extended with R0. That means this FF will sit in the LS byte of the barrel shifter's input. But it will say in the rotate saying that I am giving a E. E is what? Actually it's a 14. So it will put E here. That means this 14 will be multiplied by 2, that is 28, and then it will do a rotate right. This FF rotate, you remember this bit position, whatever comes out of 32-bit will come into the MSB part of it. So this FF will pass on and then come back like this and then process 28 bits. Why 28 times? Because only 4 bits are left here. So 28 times, if this FF moves, it should have come here. Please try to do it with a paper, then you will understand this. So what the ARM assembler has done is it has effectively allowed you to mention this pattern with the restriction that only 12 bits are allowed for the constant. Okay, so but all patterns cannot be given, but some patterns can be, and it is able to do this. Now you may wonder, can I give, instead of FF, can I give something else? Yes, of course. From 00 to FF you can give. Only thing is it should be a byte value. Okay, any pattern you have should not be more than a byte. It can sit anywhere because you have a flexibility here. You can rotate it by double the time of what you have. So you cannot do it odd number of rotation you cannot perform, but even number of rotations you can perform. Because I tell you, whatever value you are giving here is multiplied by 2 and then that many rotations are done. So only whatever values you get will be a powers of 2. Okay, let us take one more example. If I want FF to be loaded, effectively you will be, as a programmer, you will be mentioning it as this constant, and internally assembler generates this pattern and puts it into. You don't have to do this. So in assembler will put a 4 here and then FF here. What does it mean? 4 into 2, that means 8 rotation to the right. So it will effectively sitting, the FF will be here to start with in the barrel shifter, and then it will go 8-bit rotated. So it will say come back into the MS byte of the value and then goes into the ALU. Okay, so you can effectively get this pattern also implemented. Can I do this? Of course you can do, but what you do, you only rotate it by 4 times. So FF will be rotated by 4 times. So this one will be here and another 4F will come back into MS nibble. So you will get this pattern. So you can see that some patterns are possible. Instead of FF you can put any value, but you can do only some patterns. Now I have done for these patterns. Now I will give you an exercise for doing this pattern. Try it out for some time, then listen to the lecture again. Okay, is it possible to code them like this? Okay, if you have all concluded that it is not possible, you are right. It is not possible because first of all this pattern is more than 8-bit wide. So you cannot fit into this immediate constant. Whatever rotation you do, if you cannot fit in that 8-bit value, anyway you can't generate this constant. So now if you say in your code, if you use this constant, assembler will give a error that it is not possible. So you may have to use some other way of passing this value and then rotating it into 2 registers and then perform this operation. You can't do it in one single instruction. Can you do this? Can you do this? None of these combinations are possible. Okay, so I hope you understood this. I want you to try out different constants and then see the instruction generated by the simulator and see whether you can map it to this value, whether can you understand what it is doing. If you can, yes, you have understood this concept pretty well. So I am sure you will be able to follow this thing. So let me just summarize this. An assembler will convert big values to a rotated form. Impossible values will cause an error. Now assembler may also if you give move and then it may change it to MEN. If you remember MEN, I said that MEN is what? The value what you passed is negated and then passed on to the value. So if it was 0, it will negate that to FFF and then put it into R0. So if suppose you have mentioned move R0 comma this, it is not possible to do it with the previous format I showed you, but assembler will understand that okay, I can do the same thing with the move MEN instruction, so it may try to do this and it will not still give a warning, okay, but it will not be true if you put some other pattern, okay. So I am giving another example. If suppose you are given this constant to be put into R1, it will be 4 and FF will be put into the constant value and then it will perform the operation, okay. And if it happens to be EE000, this EE will be put here and then how many times you have to rotate? EE will be here, it has to 16 times it has to rotate right, then the EE will go out and come back again and sit here. Now 16 can be represented by 8 here, so it will be multiplied by 2 and then it will do a rotate right. I hope you understood this, and if you try it out multiple times, I am sure you will be able to appreciate this concepts. So I'm sorry for taking more time. I thought these are all related topics. It is better we cover it in one section. I hope you kept your interest alive throughout the discussion, and I'm pretty sure if you try out all these things, you will be really enjoying this. Okay, so this will not be covered later on. Okay, this will be appearing in any kind of operations, either AND or no, move or any data processing instruction. You will see this. Whenever you see this, you have to remember that it is on the RM operand which is coming, and then the barrel shifter is performing the job and feeding it to ALU. This you should remember always. And then apart from that, ALU will perform some other operation. But this is what you are preparing the operand for the ALU. So what all you can do is what has been discussed now. So we are ready to now get into other part of the instructions. I am sure you will encounter a lot of interesting aspects, and understanding these way things, how it is interpreted inside of implemented inside a processor, gives you a lot of idea about what you write in a high level language like C or C++, and how it is converted into an assembly and how the processor is interpreting it. So it's a very nice feeling to understand this. I hope this lecture was useful for you guys. Please try it out. I am sure you will be having a good understanding of this. Okay, thank you very much for your attention. See you in the next section. With this, we come to the end of the session 7. Have a nice day. Enjoy your lab section. Thank you very much for your attention.